Hello, my name is Thirafi Maulana. My student ID is 13118 and 238. So today I'll be explaining about the creep phenomenon. So what it is basically a time-dependent plastic deformation under a certain constant load. It usually occurs at high temperatures, which is called thermal creep, or in room temperature as well. In some materials, however, it occurs way slower. It causes strain on the material and results in an increase of length. So basically what creep is when you have a certain constant load at a material and at a certain temperature and you leave it for a high number of hours, let's say about 1,000 hours or more, a strain occurs at the material itself and has an increase in length. So there are three stages as to creep, the creep phenomenon. So the first is the primary stage, and then we have the secondary stage and the tertiary stage, and then at the end of the tertiary you have rupture. So what happens at primary is that when it starts rapidly, as we can see here, it has a rapid rate, but then it starts to gradually slow down, and as it enters the secondary stage, where it has a more uniform rate. And the secondary stage is also where 90% of the lifetime of the creep phenomenon happens. The secondary stage is also where manufacturers should be limiting their designs to. So when they're stress testing or they're testing their materials, they shouldn't exceed the secondary stage, because as it enters the tertiary stage, it is when the rupture stage. So the creep rate will accelerate and then rupture. It starts to neck as well. If it starts to neck and then it'll rupture at the end of it. So the two factors that affect the rate of creep is temperature and stress. As you can see on this graph, the low temperature or low stress has a lower rate, and as you go higher, it goes higher as well. As this actually doesn't correctly or fully represent how temperature or stress affect the rate of creep. However, it is a good generalization. It is a good generalization image as to how creep will occur as compared to how high or low the temperature or stress is. So the creep lifetime, this is the graph of the rupture lifetime as seen here, is there is a stress temperature trade-off. So a higher temperature at a constant stress materials will have a faster rupture lifetime. So if you see at the constant stress, let's take the number 80 megapascal at this point, the material at 649 degrees Celsius compared to the material at 538 degrees Celsius. The material at 649 will rupture as soon as 10 to the power of 2 hours. However, at the same stress level, the material in this blue line at 80 megapascals will rupture here at about almost 10 to the fourth hours. So it also occurs vice versa. If you have a constant temperature, let's say we'll just take this line and we'll take a different stress level at we'll take one at 50. Let's say this is 50 and we have 80. At 50 megapascals, it'll rupture at 10 to the fifth hour, which is a really long time, as compared to 80, where it'll rupture, as said before, almost to 10 to the fourth. So we have two basic creep mechanism, which is diffusional and the power law, also called as the dislocation creep. So two types of diffusional creep is Nabarro-Herring creep and cobble creep. So we'll get into details of those, but basically the Nabarro-Herring creep is what occurs at higher temperatures, and it is also called lattice diffusion. Cobble creep is the lower temperature diffusional creep, and also called as the grain boundary diffusion. And lastly, we have the power law, which occurs at a really high temperature, and it causes plastic deformation. So what a diffusional creep by definition is a changes to the chemical potential due to stress at the surface of a polycrystal grain. It is characterized by the increase or decrease of lattice planes. So we have two occurrences, as said before, the Nabarro-Herring and cobble at different temperature levels. So shown here. So the Nabarro-Herring, it occurs at relatively high temperatures. It deforms your lattice structure under influence of an imposed stress. Changes to shape, the changes to the shape are macroscopic, and this is the equation. So what it means by this is that if you have a certain grain structure and you induce some stress at a certain temperature level, the whole grain will deform, um, to the direction of the stress axis. So say um, the up and down direction is the y-axis, and you have a stress induced at the y-axis. So the grain will elongate in the y-axis, and perpendicular to that, the grain will contract. That is due to the atoms inside the grain filling the vacancy, and it'll deform the whole grain itself at the temperature. However, at cobble creep, also called a grain boundary, it occurs at a lower temperature, and why it is because it requires less activation energy. So instead of the grain itself deforming, it's more on the relation between the grain. So the boundaries between the grain are weaker at that temperature. So the grain itself will slide off each other, and this is the equation that expresses the grain boundary. Lastly, for the creep, we have power law. So the power law is also called the steady state creep or dislocation creep. The power law is a plastic deformation, and it relies on the vacancy on vacancy diffusion. There are two types or two phenomena that can occur in the power law, which is glide and climb plus glide. So what happens in glide is basically a dislocation creep is able to move sideways along the lattice structure. As seen here, this is the dislocation, and it can move sideways, and this is the glide. And a climb plus glide at a higher temperature level, however, instead of just gliding, the dislocation can move upwards as well, and and it breaks more and more of the lattice structure right here, instead of it just breaking the sideways one. Secondly, we have Larson-Miller parameter. So the LMP or Larson-Miller parameter, this is the diagram of it, which is to be used with this equation. This equation is based on the Arrhenius rate equation. And what this is for is it is used to predict the rupture lifetime when you're given the stress and the temperature of the material. So more specifically, what it's for is that it's used for stress rupture tests. So it determines the necessary time required to result in failure. It's useful for usage for dimensional tolerance or acceptable but not rupture tolerance. It is performed at a higher temperature ranges but at the same stress level. So why this is basically you want to save time for testing the material. So instead of waiting thousands and thousands of hours, you do this experiment for this test actually for less than 1,000 hours, more or less, to save time, and it is also cheaper to do so. So you do the same test at the what is it called design conditions. However, you do it at a way higher temperature, or not super high, but you do it at a higher temperature to accelerate the time because it focuses on the time to rupture. So why I said dimensional tolerance are acceptable, because when you're stress testing the creep at a higher temperature, it won't be as accurate as if you have a creep that will occur at the design condition. Let's say it's supposed to occur at 500 degrees Celsius, but you're stress testing it at about 700 or 800 degrees Celsius. So it won't be as accurate with the shape because so with that in mind, you can only use this test for situations where you don't really care about the dimensional tolerance, but you do care about when it ruptures though, so it is why I said focus on time to rupture. And from this you can extrapolate the design conditions to use on the design conditions. Next we have the heat resistant alloys. So these are the properties that they may affect heat resistant alloys. So we have two properties, so the grain size and the grain shape or alignment, where we have for the shape the equiax, directional, and single grain. So a quick explanation for the grain size is that the bigger the grain is, the more heat resistant it is. So this research is mostly done for turbine designs and turbine design microstructures. Let's see here. Let's start from the equiax grain. So equiax grains are basically grains that have similar sizes on both axes, on the x and y axis, let's say, and it can be formed by heat treatment, specifically by annealing or normalizing. This is the weakest microstructure out of the three mentioned before, as the creep life is limited by grain boundaries, because the creep can travel through the grain boundaries and it has lots of the grain boundaries. It's really weak and it's very limiting as compared to the directionally solidified, or also called columnar crystal structure. This is the difference, where this is the previously aqueous crystal structure, but this is the columnar, where the grains are all unidirectional. So it's solidified directionally, and it mitigates grain boundary induced creep. So it doesn't completely remove grain boundary induced creep. However, it does reduce it by a lot, because the creep won't be able to travel right here, because they don't have any boundaries side by side. And lastly, we have the single crystal. So a single crystal does not have any grain boundaries, and so it doesn't have any boundaries for the creep to deform to, and has better heat resistance, because single crystals are not as they're able to absorb more heat. They're more heat resistant, and it's, as said before, they're heat resistant, and it has a smoother surface as compared to the conventionally cast. So in this picture, conventionally cast, columnar grain, and single crystal. So the smoother surface, especially for turbines, has a lot of advantages. Especially, it allows air to travel more efficiently, so you have less drag in your jet planes on your turbines, and it has better. It's also better for air cooling, because your turbines will operate at a really high temperature. It has to be cool as well. As it is flying at really high altitudes, the air around it will cool it. However, if the air is a bit turbulent on the underside of the turbine, it won't cool as well, because the hot air won't travel as quickly as it would, as it's supposed to be. So that's it for my presentation. Thank you for listening, and